Hebecker, and he's going to talk about the singular bulk problem of KKLT.
Okay, thank you very much for the invitation. It's a great pleasure to speak here. And yes, so my title is the singular bulk problem of KKLT, and this is work recently finished with Xingao and Daniel Junghans, and I will also include some comments on work with Yuta Hamada, Gary Xu, and Pablo Soler. So here's my outline. So I will start with a very brief introduction about things which we all discussed, which we discussed a lot, the importance of realizing de Sitter, or even just a realistic quintessence model in string theory. And in that context, I will make a brief comment on our progress in the 10D understanding of Gaussian condension effects. This will be very brief because this will be the subject of Gary Xu's talk. And then I come to my main part, which will be the discussion of what we would like to call the singular bulk problem of KKLT. Okay, here we go. So metastable de Sitter or realistic quintessence, I would argue, are the most important challenges in string phenomenology and maybe even in the Swampland program. And let me emphasize that this is not changed by the fact that we may be having doubts about how long-lived the sitter is, whether it's only an approximate de Sitter, like Ralph suggested, because somehow we have to describe the real world, and the real world appears to have expansion. And for this, we need to stabilize moduli and break SUSY. And there we already are in a setting, even without the fundamental issue of whether eternal inflation is possible. We're already in a setting where we need models, concrete models with modular stabilization and SUSY breaking, and KKLT and LVS are the best we have. So we need to scrutinize them. Various objections have been raised about the general de Sitter and also about concretely these models. Let me only show you the list. I apologize for any omissions. And there are also many new ideas for realizing de Sitter in a positive sense. Here again are two references. I apologize for omitting many, many others. And so with this introduction, let me now come to the technical part, and let me give you a one-slide reminder just to set the notation of KKLT. So we assume we have a Calabi-Yau with all complex structure moduli fixed by fluxes. Only one modulus, a Kähler modulus, T is left. Its real part tau scales like the volume to the power 2/3. Its scalar potential is of no scale type, -3 log T plus T bar. There's a flux-induced superpotential, which is a constant, and this gives at leading order rise to a vanishing scalar potential, the famous no-scale cancellation. Now at this point, one includes a subleading effect, the genome condensation on the 7-brane stack, or instantons. We will talk about them later. Then W obtains such a non-perturbative correction as shown here, and we arrive at a stabilization in ADS. Eventually, one has to include or wants to include a small uplift due to an anti-D3 brane in a warped throat, which gives rise to a positive addition to the potential. Here, without any SUSY, just an addition, but one can describe it also in a way of spontaneous SUSY breaking. Of course, we all know and love this picture, Calabi-Yau, some cycle with a wrapped D brane, the throat with the anti-brane. Okay, so far so good. So now a key role in this is of course the exponentially steep ADS minimum. This is the thing that you saw at step 2. Here's this minimum here. It is sketched in the standard fashion, and basically it has 2 ingredients. So if you move in from infinite volume, the potential has to go negative, and that happens due to this term in 4D supergravity, W0 multiplied by e to the minus t. And if you think more microscopically, it's W0 multiplied by the Gaussian squared, lambda squared, 4D Gaussian here, which is then to condense and provide this effect. And even more microscopically, it comes from a term where the G3 flux is multiplied by psi squared, where psi is now the actual 8-dimensional Gaussian living on the brane. So this is one side of the slope. The opposite side of the slope comes from a term e to the minus t squared, which in turn comes from a quartic Gaussian term in 4D, and which in turn has to come or be associated with some quartic term of the 8-dimensional Gaussian. So surprisingly, while this quartic 4D Gaussian term is standard, it's part of the Westenberger Lagrangian or also displayed in the new Friedman von Troyen book. Its 8D origin psi to the 4 remains unclear. And so here is a proposal that will be explained in more detail in Gary Hsu's talk, where we provide a complete regularized 10D plus 80 action for this effect. So here's the first line is the kinetic term for the flux and the coupling of the flux to the Gaussian linear. That's well established. And the next two lines, let me not go into details, are the quartic Gaussian term, subtracting off a divergence which arises and providing a necessary finite piece. So I do not want to talk about this anymore. I want to say that while I feel this strengthens the LVS and part of KKLT, because these are effects which are crucial there, the simplest version of KKLT may have an entirely different and problematic issue. And I will turn now to this issue. So this new concern starts with what I would like to call the throat gluing problem, going back to a paper by Carter, Moritz, and Westphal. So for this, I want you to think about my one slide explanation of KKLT in a little bit more detail. Okay, so the ADS steps is given by e to the minus 4 pi real part of t. The uplift is also exponentially small, as given by e to the minus k over m, roughly speaking. K and m are the flux numbers on the 3 cycles of the Kepler-Strassler throat. Now, for metastable uplift to the sitter, these two potentials must match, and hence the exponents must match. So at the same time, we have the condition that the throat carries n equals k times m units of D3 charge. That is well known from the dual understanding of the conifold with fractional branes, for example. And so basically from this, you can estimate the radius of the throat, which is given just by GSN, and n is this combination of k and m. So here is a very naive cartoon of this. It's the same throat radius as you're familiar of from the famous ADS CFT n-fold stack of D3 branes. So now this gives rise to the following standard picture. So we have some Calabi-Yau, some conifold region, and the conifold region at the bottom goes over into a strongly warped region, the throat, and it's just estimated for user radius. So two things are crucial. First, we would like the Calabi-Yau radius, R Calabi-Yau to the 4, to be this modulus T. And second, our throat has to be smaller than R Calabi-Yau. Now, with this previous estimate, this leads immediately to a problematic inequality. Namely, if you just translate this inequality here into the quantities I defined before, it turns out that GSN, which is the throat radius, basically has to be smaller than K over M, which is the Calabi-Yau radius, roughly speaking. So using that K equals N over M, one can rewrite this as order 1 number being smaller than 1 over GSN. So basically, you just plug in N over M here, and you cancel the GSN factor. Now, this last inequality here is problematic. The problem is the GSM measures the radius of the S3 at the bottom of the throat, and it has to be bigger than 1 for gravity control. On the other hand, M governs the metastability and has to be bigger than 12 or even larger due to the requirement that the anti-D3 branes are metastable. So this together makes it impossible for GS, for the product of these two numbers, to be parametrically small. And so the standard picture of a small throat glued into a large bulk Calabi-Yau cannot be maintained. So now the question is whether this is already deadly. And I would say not yet, since a priori the warp factor of this model can come to rescue. So I remind you that the whole story is, if you look at it in a bit more detail, not Calabi-Yau, but it's warped Calabi-Yau. So there's a warp factor here inversely in front of the 4D part of the metric, and then there's a warp factor square root of as a prefactor of the Calabi-Yau metric. The twiddled quantity is just the standard Calabi-Yau metric. So the Kähler modulus in this language corresponds to shifting the warp factor by a constant. And you can do so by negative or positive constants. It's a flat direction as shown in detail in the famous paper by GKP. And so we may simply make the bulk smaller than the throat. Nobody stops us subtracting so much from the warp factor that a picture arises like that. So here left, you have the marginal situation, a very big throat glued into a Calabi-Yau, such things just fit. Now, if I make the warp factor even smaller, in the Calabi-Yau, the cycles continue to shrink, the warp factor will grow towards the throat, and here the throat can still have its necessary size. So everything looks conceivably okay. So now comes a singular bulk problem. So the problem is not that this geometry defies our standard intuition, or that it looks strange, if you wish. It is that the Calabi-Yau may be forced into a regime where in a large part of it, the warp factor actually turns negative. And negative means that you have an actual singularity because there's a square root of h in front of the Calabi-Yau metric, or the warped Calabi-Yau metric. So this danger of growing singularities has already, in fact, been emphasized or in the appendix of the Carter paper, but without turning this into a quantitative problem for KKLT. And so what I want to do in the rest of this talk is to demonstrate that, in fact, generically, the regime of KKLT enforces negative h, not in some places, but in a large portion of the total geometry. Okay, let's do that. Or let's see whether we can give a precise argument. So first, as a reminder, of course, the behavior of the warp factor is well known in the vicinity of D-branes or O-planes. For simplicity, I will look at the case at the moment where there's a negative tadpole necessary for this construction arises from O3 planes. But of course, it can also arise from curved D7 branes. Nothing would, I mean, the argument will go through. So near D3 brane, you very well know the warp factor diverges, and you get the famous ADS CFT geometry or ADS 5 times S5 geometry on supergravity side. Near O3 planes, the opposite happens. This is positive charge, this is negative D3 charge. Sorry, apologies, I jumped too fast. Here, the warp factor goes to minus infinity. Oops, before doing so, it crosses zero. So there is a singularity here. But nobody believes this is a problem because we know that in O3 plane is string theoretically consistent, and the singular region is a very small string scale size region near the O3. So what I want to argue next is that the situation is not like here on the left, where you have a tiny singular region near the O3 and the rest of the Calabi-Yau is okay, but it's more like that, where the singular region is large and it swallows up a large part of the Calabi-Yau and generically even the D7 brane with a Gugino condensate. And this is a problem for control. All right. So for quantifying this problem, for explaining this, a key insight is that the exponential effect is in fact determined by the size of the warped E3. Let me, for simplicity, I will turn to D7s later. At the moment, focus on an E3 instanton. So there's some volume of this wrapped brane, and our previous equality or approximate equality needed for consistency of KKLT was real T equals n over GSM squared. And so because this real part T is the volume of the E3, we, roughly speaking, have this relation. So the volume of the E3 has to be n over m squared. Now the volume of the E3, in this case, has to be measured with a real physical metric. I mean, that's what governs the tunneling process of the E3 instanton. So here we have the integral over the Calabi-Yau metric and the warp factor over the E3. And you can think of this as being the unwarped E3 cycle multiplied by the warp factor averaged on the E3. So without loss of generality, we can now do the Calabi-Yau metric normalized to unity. And then we expect that also the E3 volume in the Calabi-Yau metric is an order 1 number. I mean, it is the only 4 cycle of this geometry. So basically what we are doing here is we are constraining the warp factor on the E3 cycle, like in the red box here, right? The average warp factor on the E3 has to be n over m squared. Good. So now At the same time, our quantity H, the warp factor, solves a Poisson type equation. That is, again, well known from GKP. I wrote it down here. The source is the D3 charge. And the normalization is such that it is GSN for n units of D3 charge. So basically, H is a compact space Green's function for a certain charge distribution. And we know what that charge distribution is, at least qualitatively. We know there are GSN units of positive charge localized at the conifold, at the tip of the conifold. And there are minus GSN units of negative charge, which have to be scattered somewhere in the Calabi-Yau. For example, O3 planes or curved D7s. And given that, you immediately know what the typical variation of the solution to this Poisson equation will be. Namely, it will be some order 1 number scaled by the size of these charges, GSN. Now, at the same time, it has to be combined with our knowledge that the value of the warp factor, of the average warp factor on the E3, is n over m squared. So what we find is the value of H is small near the E3, much smaller than the average variation on the Calabi-Yau. And that, as you see in this picture here, at the moment only intuitively, leads to a generic problem. Namely, you have here a function which is kind of a very naive toy model function for the solution of the Poisson equation, pardon me. So it diverges near the throat, and then it has to somehow have a smooth behavior because the tadpole is compensated in the bulk. It has to have some small value at some point in the bulk, which I don't get to choose. This is a point where the E3 cycle sits. And then this number being smaller than the average variation of the function, it's clear that beyond that point, you generically very quickly go to negative regions. There's simply a strongly varying function which you chose to be equal to a small number at a given position, and then beyond that position, it goes negative. So in different words, let me put it differently, you can estimate the ratio of the derivative of H to the value of H as the E3. And this ratio is large, much larger than unity. And then you can Taylor expand around a point y0 of the E3. And you see at the leading order Taylor expansion, there's some constant value plus the leading order term. And you see, because its derivative is much bigger than the value here, you get to negative values, at least in one direction of y, very quickly. Very quickly means at a distance which is small compared to the total Calabi-Yau size. So H runs negative near the E3. Again, the intuitive picture here. Let me give you an alternative view of this problem. The alternative view is that you simply calculate the curvature induced by the warping. Before warping, it was 0 because it was Calabi-Yau. And you can just work out the numbers, and you can use our estimates for the variation of the warp factor from the Poisson equation. And you get that to have this Ricci scalar on the Calabi-Yau smaller than unity. It can be in principle be achieved, but it can be achieved only in the regime of such a large tadpole that it exceeds the best models with the largest tadpole that are known. So you simply do not manage to get this geometry at the strong warping which is needed to be sufficiently tame, sufficiently weakly curved. And crucially, all of this applies also, or most importantly, to the coarse-grained warp factor. I mean, I try to make a sketch here that there are many O3 sources scattered through the Calabi-Yau. At each of them, the warp factor goes negative, which is not a problem. But even some kind of coarse-grained average warp factor will turn negative in a large region, simply because the accumulation of tadpole is so large. Maybe I should, at this point, describe this a little bit better in the toy model. So, of course, our real desire would be to understand this in a proper Calabi-Yau. But this is beyond reach at the moment. And so let me make the following model. Look at this top picture here. So there's a sphere. I take a 6 sphere as a model of my Calabi-Yau. I put here in symbolically this little nose is the throat. At the throat, I put some charge, GSN, in my previous notation. And the rest of the charge, the negative tadpole, is scattered homogeneously on the sphere. So now in this case, I can parameterize the motion from north to south pole of the sphere through an angle phi, going from 0 to 2 pi, and I can explicitly solve for the warp factor and plot it. And as I shown before, the warp factor, of course, diverges near the not. It doesn't. Yeah, it actually diverges, but of course, then it's cut off by the Kleppner-Strassler region. But as long as I don't resolve the conifold, it's just divergent at the stack. Then it goes down. It goes down.
So you're left with 5 minutes.
Sorry,
you're left with 5 minutes.
5 minutes. That's perfectly fine. Then it goes down, 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 and ends with some finite value. There's no divergence on the other side because the competing charge has been smoothly spread through the sphere. And then if I want this to be some small number at some given place, then the only freedom I have to achieve this is the overall up and down shift of this warp factor. This is not fixed by the Poisson equation. This is my constant, my Kähler modulus. And so I'm forced to fix this function such that it runs negative. And immediately you see that there's a way out. The way out is that I can put all my O3 planes as a ring, as a little ring here near this rod. Then my function gets saturated faster. Here the tadpole is saturated and there's no O3 distributed here and the function remains constant. That would give me a non-singular situation. But it requires me to compensate the tadpole of the throat immediately once I enter the Calabi-Yau. So what are escape routes? So one option suggested by the model I just showed, by the toy model, is a very special arrangement of O3s or curved O3s to 7. It looks extremely challenging to claim that or study that in Calabi-Yau geometry, but maybe possible. Very ungeneric. Another option is to observe that the problematic small parameter changes if I replace the E3 by Gugino condensation. Namely, this 1 over GSM squared, which I would like, which is small, but I want it to be large, changes to NC over GSM squared. However, I can not use large NC without having to pay a price. And the price is, according to these analyses, large H11. But large H11 is problematic due to the scaling of Demeters et al. Namely, if I have very many cycles and I want the smallest 2 cycles still to be large, controlled, then the 4 cycle volume scales like H11 to some power, to some relatively high power. And so one ends up with a requirement on tau being so large that again, one exceeds the total tadpole. So it is hard to see how that would be realized. There are some very specific routes of combining large H11 and large NC, which may work, but it looks extremely challenging. So a logical possibility, which is very interesting, I think, is just to accept the singularity and see how string theory resolves it. So in a simple case, namely 7th wrapped in K3, this has been analyzed recently using F-zero inspired dualities by Carter and Moritz. And they find or argue that there is a non-singular but strongly curved geometry appearing in the region where you think the warp factor goes negative. But the problem is that then, at least in my understanding, one simply loses control of the classical Kähler potential. And it is very hard for me to see how one could repeat the otherwise very convincing controlled analysis of KKLT in such a strongly curved situation. Okay, in fact, that's it. So I think I'm pretty much in time. So let me go through my summary conclusions. So the first thing is one should not simply believe in metastable stringy de Sitter being possible or impossible. One should try to demonstrate it. I would even go beyond. I would say that even if one is convinced de Sitter cannot be done, one still needs to realize some kind of geometry with approximate de Sitter and SUSY breaking, as our real world is. And then all these problems have to be faced. So I think it remains a very important problem, even for skeptics of eternal de Sitter. So concerning the 10D line of attack, things appear to work out in favor of KKLT and LBS. And again, I would like you to look at more details in Gary Hsu's following talk. However, KKLT, I would argue, may fall victim to what we call the bulk singularity or singular bulk problem, which I just explained. And the escape routes appear complicated and non-generic, but I admit that this does not make them hopeless. And however, an important remark is also that even if KKLT should fall victim to this, the LBS appears not to suffer from this issue. And I think that brings me to the end of what I was going to say. Thank you very much for your attention.
Thank you very much, Arthur. We can all thank Arthur for the nice talk. Any question for Arthur? You can ask in the chat or raise your hands. I don't see any right now, so let me ask one actually. It's a very basic one, but you insist in this conclusion and in the introduction on getting a metastable string de Sitter, but how about, I mean, why metastable actually? I mean, if we want to get quintessence, for instance, we don't exactly need this actually. We could allow some flexibility.
You cannot, yeah, that's a very important question indeed. Thank you. So we studied this, and I had no time. I decided not to advertise our paper and our work on this. It has been, in fact, been known. We just added details, basically. I mean, you cannot simply take the volume to run away to have quintessence. If you do that, you run away much too fast. I mean, our SUSY breaking in the real world drives you to run away too fast. So what you do if you want to make realistic quintessence in the framework of things we understand now, is you have your volume still stabilized in SUSY breaking, everything that you know and love from KKLT or LBS, and then you need to find a different field. For example, some extra Kähler modulus, some axion that runs away and plays a role of quintessence. Then you can live happily with the generic arguments against de Sitter, but you still need to know how you stabilize your Calabi-Yau in the face of at least TeV scale SUSY breaking, and that challenge remains. And so it still remains a highly non-trivial challenge. It's not, you don't get anything for free in this case. Well, thank you for the question. It's a very important point indeed. I would love to speak longer, but I see there's another question from Pablo.
Yeah, thanks. I agree with what you said. So yeah, Pablo, please go ahead.
Hi, Arthur. Just a question about the statement of how generic this problem is. So you say it's you need a very special arrangement of charge, but how bad is that? If I could scan over Calabi-Yaus and all their distributions, I would probably find some sectors of those where
I'm very sympathetic with this. I'm very happy to believe it. I just wanted, I mean, yes, one could give a much more optimistic talk about this. However, to me, in my naive thinking, it was such that KKLT is already a fully controlled model. You know, it just generically works with one cycle and no special things. And the only thing I put in is that I'm able to tune W0 very small, okay? And that one parameter I thought was sufficient, and upon careful study, I was shocked to see that it isn't. That you need further non-generic features for this to work.
Right,
so I was myself surprised, but if you say it like that, I'm happy to believe that somebody can find a special arrangement where things can work out. It's just a different level of explicitness now.
Yeah, but I was gonna mention W0. We know W0 small is not generic, but it's possible. So if we
yes. So I need a further non-generic. Okay, good, very good. I'm happy to formulate my things very much more optimistically. Surprisingly, in addition to the known need to make W0 non-generically small, I have a further need to make the O3 distribution non-generic, such as the Calabi-Yau is not destroyed by the strong warping. Very good. I'm happy to.
And just a small add up, the gluing problem nevertheless would remain.
The throat gluing problem in this case remains, but it's not a problem because it only means that the geometry is very kind of puzzling. You know, the geometry just looks like my best drawing abilities are shown here, right? You have some small Calabi-Yau and the warp factor grows, and then goes over in the KS throat. And it looks very strange because the Calabi-Yau cycles are smaller than the radius of the throat, but there is nothing wrong with such a geometry as long as you make sure the warp factor does not actually go negative. It's just small here and big here, and I can make that work.
Thank you.
Okay, Joseph, I give you 1 minute, one question, one answer, if possible.
I actually had a question. I asked it in the chat, and Daniel answered it partially, but I'm still a bit confused. It's exactly about the picture which Arthur just showed. I mean, the one on the right with the H growing and then with the KS throat. So the way I see the picture, I mean, you know, normally if I have empty space and I have a piece of the space growing and then shrinking without anything there, this tends to violate all sorts of GR theorems and so on and so forth. So, you know, that's why in Klebanov-Strasler, for example, the throat size keeps on growing and growing and growing. And, you know, if you glue Klebanov-Strasler to flat space, it keeps on growing and growing and growing. The only way to stop the sphere size from growing is to actually get some topology there, which is actually going to shrink your space and allow you to become compact. So I don't think you can put the topology far away and then just hope that the sphere is going to grow and then at some point shrink. I don't think this can happen at all. And I think there are some GR theorems, I'm pretty sure that, one can sit down and, find immediately why this is a problem. The only way you can have this picture is if your topology stays exactly at the point where the size of the sphere starts, where the size of the sphere is near the.
I agree with your concern. I think that I agree topology could be such that you simply, identify boundaries and things are like you explained, but I'm not sure to which extent the negative tension of the O3s actually may help. So here in this region, there's actually negative tension scattered through the space.
Sure, if you put that, I think that's reasonable. If you put that, this is going to violate all these theorems, absolutely.
Yes, so negative tension is crucial to be able to draw this picture, I think. And admittedly, I have not done anything except the toy model where you can see the effect exactly like that. But the toy model is, of course, wrong because the sphere has its own curvature. That's a problem. I mean, it would be very exciting to study something as crazy as this geometrically. Yeah, thank you.
Sure, thanks.
Thank you very much, Arthur, for the very nice talk and for the questions to everybody. And we will now move on to